Good evening, everybody. I'm Pete Littlewood. It's my pleasure to chair this evening session. We have a talk here on visualizing quantum matter, as you will see. I think I'll say a bit of words about visualizing matter because this is St Andrews, and St Andrews is home to Brewster. Those of you who know about Brewster will know about Brewster angles, maybe, and it's associated, of course, with the diffraction of light. It explains why, if you're very careful, you can fish, and the fish can't see you. But it also has to do with the study of crystals, because Brewster understood, although he may not have known very much about crystals, he certainly understood how they diffracted light and how there were certain angles associated with crystals. Crystals have their shape because there are atoms, and atoms packed together in particular ways. I'm not sure how well Brewster would have understood that, although I think it was widely believed at that point that there were such atoms. I think it wasn't perhaps ever imagined that one would be able to look at atoms and see them one by one, and not just to see them one by one, but to measure things about them, namely, what is their color, what is their shape, what is their energy, how do the electrons jiggle inside them? Of course, electrons weren't even known. And our speaker tonight is going to tell us all about that, because Seamus Davis, the distinguished lecturer this evening, is in fact one of, if not the, renowned experts in doing all of those things, in looking at the structure of atoms on the surface of the solid, many interesting and different kinds of solids, and he's going to tell you about that. To introduce Seamus, just briefly, he is Distinguished Professor of Physics at Cornell. He is also a scientist at Brookhaven National Laboratory. He is a, I believe, Distinguished Professor at SUPA, Scottish Universities Physics Association, so he spends quite a bit of time researching here. He is the winner of the Fritz London Prize, the Cameron Honest Prize, probably quite a few others, but I remember those two. And he's a member of the National Academy of Sciences. I'd like to welcome Seamus.
Okay, can everyone hear me? Yes. Okay, how many people sitting here are professional physicists who have been sitting here since 9 o'clock this morning? Put up your hands. Okay, that's more than half. All right. Well, thank you all very much for being here in that case. It's been a long day. I would encourage you to ask me questions, but remember, I'm the one between you and the drinks reception, so every question you ask me delays your opportunity to get out of here. I took a careful look at the amazingly interesting program for this scientific conference run by Topmas here today. And I decided, certainly I'm going to talk about visualizing quantum matter, but I just want to talk about quantum matter itself, because that's the central theme of what's going on in this conference. So let's review our progress a little bit. So for the last 5,000 years, we have been trying to develop quantum matter. Let's see, so here are various people who we could discuss if you wish, some more infamous than others, but they just represent, in my mind, various historical epochs over the last 5,000 years, during which we have written records of how people thought about scientific ideas and the use of materials for the benefit of mankind. Okay, so during that time, development has gone from this is the Neolithic age, the post-Mesolithic age, where detailed tools were being made by using special types of stone. Then a transition to the Copper and Bronze Age. Most people don't know, but the Copper Age was very long. It was like 1,000 years long, during which people didn't have bronze. And for example, the pyramids were built not using bronze tools, but just using copper tools, if you can imagine that. Then a transition to the Iron Age, and then, you know, growing attributes of civilization, at least around the Mediterranean Sea, in terms of ceramics, One of the greatest technologies of the Romans was cement. They're not very well, they're usually remembered for violence, but one of their greatest achievements was cement. And the reason why much of their architectural heritage survives is that they had wonderful cement. So then going through the development of iron and steel, and then through the steam age, steamships, steam trains, skyscrapers, all dependent on better and better steel, to the modern world. Very, very recently on this scale, we transitioned to the Silicon Age. Now, these are materials. Most people are not interested in, well, geologists are, but most people are not interested in materials because they're materials, and some physicists are. But what everyone is interested in is information. Most of the major revolutions in all the various societies over this time were triggered by access to information. So starting with cuneiform, hieroglyphics, scrolls, papyrus scrolls written in many languages, through handwritten books, Gutenberg printed books. Once this explosion occurred, the rate of change of society became very, very fast, because information is the thing that feeds those changes. And look at this thing. It's less than 10 years ago since we changed over to electronic books. The rate of change is still increasing. So we certainly have come a long way, and the question is, where are we going to now, and how are we going to get there? So I have to tell you a little bit about what materials are made of. So this is a piece of material. Any Irish people in the audience? That's Jimmy Barry Murphy. Okay. He is made of objects, cells. There are a few microns in size. Running those cells is DNA. There are a few nanometers, 10 to the minus 9 meters in size. The DNA is made of atoms. Each atom is a few angstroms, a few by 10 to the minus 10. Inside the core of the atoms is the nucleus. It's a few femtometers, 10 to the minus 15 meters. In each nucleon, proton, or neutron, there are 3 quarks. So at the end of the day, everything is made up of the stuff in the nucleus and the electrons surrounding them. That means there's only 3 objects making up all the matter in the universe. As far as we know, there are only 3 stable objects in our universe. There's 2 quarks and an electron. They make everything. Well, they don't make absolutely everything. There are neutrinos, which are flying through us all the time, but we don't perceive them, and they have little impact upon us. And of course, there are various bosons, like photons, which we use to exchange information with the world around us. But the stable objects are just 2 quarks and 1 electron. They make all the matter that we're familiar with. There's a boatload of other matter in the universe called dark matter, but nobody knows what it is, and I certainly don't. But I do know it's not made of these 3 objects, so that's some progress. The reason why the universe is so complicated, if it's just made of 3 objects, is because of quantum mechanics. The rules of quantum mechanics are very strange. Oh, I wanted to make another point. This is for my Irish colleague. So these 3 objects have names. They're called quarks and electrons. And where did the names for the elementary particles in our universe come from? Well, they came from Ireland. George Stoney, who was a competitor of Clerk Maxwell's, named the electron in the late 1800s. And of course, James Joyce is the one who coined the word quark, which was then used by various famous particle theorists, but this word appears in Finnegan's Wake. So quarks and electrons, their name comes from Ireland. We're very proud of it. Now, if you take those guys and put them together using the rules of quantum mechanics, you can get some very, very strange and exotic matter. You can get the list of 100 plus elements, which we now know and understand very well. And from those elements, in the different ways that they combine, we get the materials which now dominate our way of life. Here's one example. You take exotic materials, you put them together in a very clever way, and you get one of these modern miracles of modern technology. Inside an iPhone or inside a Galaxy phone, there's several dozen different elements One of the largest things in there, as you probably know, is the battery. It's built on lithium and cobalt and oxygen with graphite and aluminum surrounding. The electronics is built on silicon doped with phosphorus, and the wireless part that you use for telephone calls and to get your data is built on gallium and arsenic with various dopants of these two atoms. The package is usually made of aluminum or borosilicate glass. Your phone can make very loud noise and large mechanical motions. How does it manage to do that? It uses high field magnets inside, which are made of neodymium and praseodymium, boron and iron. Many of these compounds have only been invented in the last 50 years. The screen of your phone, it senses your finger because it's actually a conducting, even though it's transparent, it conducts electricity. It's got an indium oxide layer, which is conducting but transparent. And then it's got a silicon actuated liquid crystal, which is the thing that we all look at to get our messages, etc., etc. It's hard now to tell what's in the liquid crystal displays. They're all secret. They're worth billions of dollars. It's actually difficult to find out which species of liquid crystal is in a modern phone. All right, so if we've reached this point now, what's next? That's the purpose of this conference, to try and explore some of the ideas for what could be next. Now, one possibility is we just keep going the way we've been going. We just use more and more elements in more and more complicated combinations to make more and more complicated electronic and automotive and air devices, etc., etc. But there are many engineers who believe that can't go on forever. There are practical reasons why there are limits to that process, which we have been using now for the last several thousand years. So the alternative is to change over to a quantum basis for our technology. So to discuss that, we have to discuss quantum mechanics. Here are the three pioneers of quantum mechanics, Schrödinger and Heisenberg. They basically proposed that every particle in our universe is actually not a little bullet, it's a wave. And the wavelength is related to the momentum of the particle, p is the momentum, through a number which is called Planck's constant. And it's a very tiny number. So the wavelengths are usually very tiny. And every wave also oscillates at a finite frequency. The frequency is related to the energy of the particle through Planck's constant. It was Einstein who proposed this equation. Okay. Now you say, I don't see those waves around me every day. Why should I believe they exist? Well, you can do experiments. Most physicists have done these experiments in their training or for their research. For example, you could take a source of electrons, shoot out the electrons into this space, and then have two openings. They're called two slits or two apertures. If each electron were a wave, then as it exits from the slit, it'll travel off as a wave. But these two waves are coming from different sources. So they'll interfere with each other, making an interference pattern. Some places the waves add together, making a strong amplitude wave, and some places they add destructively, making a weak wave. Now imagine you're God, okay? You want to look at this quantum mechanical wave and decide what's happening. So it's not like watching a wave from the North Sea approaching the shore, because the object which this wave represents is actually a particle. When you detect the particle, you're going to detect it at one location. And that was a profound difficulty in the beginning of quantum mechanics. Max Born is the one who, at least philosophically, solved that problem. Oh, and many of you know Max Born spent the second half of his career at Edinburgh, which is where he was when he received the Nobel Prize for this proposal. Namely that these quantum mechanical waves, if you square them, the amplitude squared is the probability that something will happen. So where the amplitude squared is big, you will detect electrons, and where it's small, you'll detect none. Now, if you do this experiment, it's been done millions of times, that's exactly what happens. Although this theory doesn't make any intuitive sense, although it doesn't make any intuitive sense to me, it's an excellent predictor for how nature works. So the universe apparently is run by these Schrödinger-like waves, and you can detect them by detecting the statistics of individual particles. People had not considered how to detect the waves themselves, how to visualize the waves themselves for many decades. One of the things we've worked on is how to visualize these guys. Okay, the other thing I have to tell you is if you put a particle in a box, suppose you play racquetball, let's say. You're in a box, or squash, sorry, this is the UK, so suppose you play squash. You're in a box, and it's got a ball with energy and momentum in it, and it shoots around and it hits you and your competitor and so on. But that's our classical view of this situation. In quantum mechanics, that particle is a wave. And for it to be bound and localized in that box, that wave has got a certain amplitude related to its, wavelength related to its momentum, and frequency related to its energy. If you put the quantum mechanical object in the box, and if everything is governed by quantum mechanics, what you would detect is the space and time dependence of this wave for the particle. Okay. Now, quantum information is one of the most exciting subjects in modern physics. The reason why it is so intriguing and stimulating is that if every object is wave-like, okay, if every quantum mechanical object is a wave, a property that waves have is that they can be added together. When two waves approach each other, they don't annihilate, they just add together at the location where they're passing. So if every quantum mechanical object is a wave, then you can add different objects together in a way that you can't in the classical world. So Schrödinger is the one who first was really worried about this. And here's his famous cat. He said, suppose you have a quantum object that can be in two states. Physicists would say it's in state up or state down, but to make it more amenable, Schrödinger said the cat is either alive or dead. But you can make a quantum mechanical state where it has a certain probability to be one and another probability to be the other. You can make it a combination of both states. Now that's called a superposition. We know for certain that this happens. We don't know that it happens with cats, but we know that it happens with objects made of thousands of atoms, and certainly it happens with individual quantum mechanical objects. Now here's where it gets really scary. Take two cats. And take each cat and put them in a combination of the two possible states. Okay, so this is one quantum mechanical state and this is the other quantum mechanical state. That just looks like a copy of the thing I already told you about. But now if we write that down mathematically, we have a certain prefactor multiplied by this state, a different prefactor multiplied by that state. There they are. Same for this one. But now a combination of these two identical objects, which we now call qubits, is also a perfectly valid solution to the equations. So you can make a quantum mechanical object where this guy and that guy are mixed together, they're so-called entangled, such that all four possibilities, both cats are dead, both cats are alive, one is alive, one is dead, one is dead, one is alive, they're all governed by quantum mechanics. This is an entangled situation. The thing which is going on here, which is really interesting, is the number of possibilities grows very rapidly in quantum entanglement. Einstein hated quantum entanglement. He hated it with a vengeance. So just about 80 years ago, he launched his final attack on quantum mechanics and quantum entanglement. And it was, at the same time the paper was published, there was a front page article in the New York Times saying, Einstein destroys quantum mechanics, or something like that. You can read it for yourself. So Einstein's argument was you could take two objects, let's say two cats, and put them in a well-defined state. Now, we now call this a spin zero state, but it just means one of them is, let's say, alive and the other is dead. You're guaranteed that that's the initial state, but that's all you know. Now, you don't know which one is which. Then you separate them, allow them to depart from each other, but remain quantum mechanically entangled. And after some time, you measure the state of this guy and write down the answer. But according to the theory of quantum mechanics, because it's entangled, instantaneously the state of the other guy will be found to be in the opposite spin direction, or if this is dead, this one will be found to be alive. Instantaneously. There's no propagation time in measurement theory in quantum mechanics. So Einstein's deduction was that since the theory says that this would happen instantly, that violates special relativity, which says nothing can travel faster than the speed of light. So he deduced from the fact that he was right in the theory of special relativity that quantum mechanics was wrong, which was an interesting way of thinking about it. Okay. He postulated that there's a missing piece to this theory, and the missing piece is called a hidden variable theory. And this word local just means that Still, nothing travels faster than the speed of light. So we don't have a complete theory of nature, we just have there's a hidden part to the theory remaining to be discovered. Now this is John Bell. He was a very determined, self-actuated man who didn't really accept received wisdom, even if it was coming from Einstein. And he was also extremely curious about this problem. And he was also Irish. So, so he made a predictive way. He designed a way to do an experiment to test Einstein's proposal. That experiment, the Bell experiment, has been done billions of times since he proposed it in the 1960s. And for all of those times, what has been found is that the predictions of quantum mechanics are always observed to be correct. And furthermore, you can prove from the logical structure of Bell's theory that there's no local hidden variable which could ever explain quantum mechanics. Now, you could have a non-local hidden variable theory, but that would mean that special relativity is wrong. So we're stuck in an awkward situation. Furthermore, people have been testing. You entangle two photons, you measure the polarization of one, and let's say 500 kilometers away, you simultaneously measure the polarization of the other. This is done all the time now. You'll always find a perfect within the signal to noise, one-to-one correspondence for the opposite state between this one and that one. Such that if you were required to send the information to control the outcome of the second experiment, you'd have to send it at 10,000 times the speed of light. That's a fact. So this entanglement is very, very strange, and although you can't send any, no one has figured out how to send any information with it, nevertheless, it seems to be a fundamental part of physics, which transmits correlations at infinitely high speed. Now, why are we interested in it? Okay, so this is Boole. Boole is the one who figured out the binary logic, which is behind all of modern digital computing in the mid-1830s. He died as a young man. He got the flu, and his wife advised him, oh, he's Irish. His wife advised him to take cold baths when he got the flu, and he died as a young man. But unfortunately, fortunately, he had figured out Boolean logic first. Now, the thing about Boolean logic and data processing as we use it now is that essentially, roughly, if you want to deal with n bits of information simultaneously, you need n logic elements, right? If you want to process 1 billion bits simultaneously, you need 1 billion transistors. That's why we're now, all of us, using devices with billions of transistors in our back pockets. The only way to keep growing the rate at which we can interact with information, let's say through handheld devices, is to increase the number of these classical transistors in our present technology base. Moore's law says that you can get more and more and more transistors onto the same chip. And it implied, and of course, Moore also is of Irish extraction. I know him. It implies that you just keep putting more and more and more transistors on an object the same size, let's say the size of your fingernail. The truth is, though, that stopped working already about a decade ago. The size of the CPUs in commercial devices is now 4 times bigger than it was then. Because the only way you can't make the transistors any smaller. The only way to make our present information technology work is to make the region where the electronics is living bigger. And the reason is the atoms and molecules are finite size. You can't make a transistor from half an atom. We will reach that limit. So how do we get out of this trap? Well, entanglement is how we get out. Suppose you have a qubit. It's a quantum mechanical object with 2 states. So what? Suppose you have 2 qubits and you entangle them. But now there's 4 states that you can work with. 4 logical pieces of information from 2 devices. Now suppose you take 3 qubits, there are 8 states that you can work with. Okay? The number of states in the system is 2 to the power of the number of quantum mechanical devices. If you have 300 fully entangled qubits, you would have more data under your control than there are particles in the universe. This is the deep reason why quantum information technology is so important for the future. Now, the engineering challenges to do this are absolutely horrendous. People have been trying to do this for decades. They're really difficult. But the vision that one should do this and convert from classical, sadly dare I say it, Boolean logic to quantum mechanical logic, now is the time when we actually have to do it. The record for entangling quantum mechanical objects in a solid state physics device is 7 bits. It's held by John Martinez's group, which formerly were at the University of California at Santa Barbara, but they were recently all hired en masse by Google. So you can take that as an indication of whether people are serious about this business or not. All right, second thing I want to talk about is quantum matter. This is closer to my own interests, but it's related in the same way. The entanglement of identical quantum mechanical particles is producing very new strange states of matter. Now here are some conventional states that many of you would be familiar with. So here's a metal. That's actually Shoshank I's signet ring. He invaded Canaan about 3,000 years ago, unsuccessfully, so his ring was found in the ground outside Jerusalem. So here's an insulator, diamond, magnet, semiconductor. Faraday discovered semiconductors in the 1840s. So that's the real time between fundamental discovery and, commercial devices, 150 years. We also use a lot of ferro and piezoelectrics in our technology. The most familiar one to you would be the trigger that fires the airbag in your car. I hope it never has to fire the airbag, but it uses piezos to do the accelerometers. And superconductors, which are materials that can conduct electricity in a perfectly dissipation-less fashion. I also regard most of them as fairly conventional materials. Now, just bear with me for 3 minutes. I need to tell you a little bit of physics here. If each particle is a wave, the wavelength, so here's the momentum of the particle. It goes as 1 over the wavelength. The energy is the momentum squared, okay? So, if I square the momentum, it goes on a parabola like this. So that means high energy states have short wavelength, and low energy states have long wavelength. If you put electrons in a crystal, that's the world they live in. In the crystal, there are atoms at a fixed periodic distance. And when the wavelength of the electrons reaches the same distance as the distance between those atoms, then it disrupts this world of free particles, and it opens these so-called energy gaps. And those are energies at which no electron can travel through the material. Based on those energy gaps is where our silicon, gallium arsenide, semiconductor information technology comes from, because for a given crystal, we can figure out what all the energy to wavelength relationships are, and we can put the correct amount of electrons in the material to have it achieve the material properties that we wish. So it's on this basis of these bands that our semiconductor technology works. Now, think about it though. Those are some familiar states of electronic matter. But how come there aren't many other kinds of electronic matter? Is there some rule that says these are the only ones that can exist? No, absolutely not. There's a whole variety of other states which could exist, and some of them have recently been found to exist. Here's the reason why. So this is a traffic jam. If you drive to Edinburgh in the morning, you know what this is like. So what happens here, what controls this situation is the dimensionality. You're in one plane. If you could fly over the car in front of you, there would be far fewer traffic jams. But you're constrained to this plane. Now, your insurance company wants to enforce a so-called no double occupancy constraint. That means no 2 cars are at the same location at the same time. Okay, that's no double occupancy. If you put enough cars on the road and you enforce that constraint, you get a traffic jam. If you remove a small number of cars, the traffic flows in a somewhat unpredictable fashion. But if you're a driver, you can't do anything you want. What you do is contingent on the status of all the other cars surrounding you. That's called a correlation. So this is a classical, strongly correlated system. Now imagine this with electrons. So here's a crystal, here's an atom. It's actually a copper atom in this diagram, but it doesn't matter. We put one electron at each one of these copper atoms. And now arrange it so that the energy for 2 electrons to occupy the same atom is so large that it'll never happen. Then you get a quantum mechanical traffic jam. No double occupancy will freeze these guys in position. That's not, you can get the Nobel Prize for explaining this, which Mott did, but it's not particularly useful. However, if you remove a few of the electrons, so that there are empty spaces, they're called holes, then some of the frozen electrons can move. But the motions they can undergo are a function of the arrangement of all the other electrons. So that's called strong electronic correlations. Many, many, many materials, uncountable materials, have this property, that there are very strong correlations inside. But we haven't used those materials very much in our technology base until now. They produce all kinds of exotic and unprecedented forms of electronic matter, high temperature superconductivity, super heavy electrons. Piers Coleman talked about this morning. Quantum critical states of matter, he talked about that as well. They also produce colossal thermoelectricity, which is something very useful for getting power from heat. It's important for modern energy harvesting, and many other strange states of matter, but they're poorly understood. The number of possible materials we could have, which are in this strongly correlated list, was huge. And then recently, with something called molecular beam epitaxy, you can make artificial materials which would never form naturally. So the number that we can imagine now is absolutely enormous. It's uncountable materials that could have these strange properties. Okay. Now I want to motivate for you an example of a new type of electronic matter, which is being driven by these strange properties. So here's a vapor. You're probably familiar with it. It's called steam. And it has very few properties. You know, if you look at it from any side, it looks the same. It has no internal degrees of freedom, no weird properties. Now, if you take the molecules, the H2O molecules, and you make them interact with each other more strongly, you'll get a liquid. Water is a very strange liquid. We're mostly made of water, and we're very strange. And so that's, but water is actually quite hard to understand because there are strong interactions, but the system hasn't yet frozen. So increasing the interactions makes exotic liquids. Now, most of you, if I ask you, if I increase the interactions some more, and especially if I cool down, what would happen next? You'd say, you'll get ice. You'll get a crystalline state of those molecules. But in general, that's not true. There's another state which intervenes. It's liquid crystal state. Cholesteric liquid crystals were discovered in Zurich in the 1890s, and they didn't become commercialized until the 1970s. This state partakes both of properties of a liquid, the molecules can move around, and of a solid. There's some spatial patterning of the molecules. So liquid crystals, as you now know, are critical to our modern technology, and they're a very large part of the world economy, trillion-dollar economy, making liquid crystals for us all to spend our time looking at them. If you have teenagers, you know that they can look at n different liquid crystals simultaneously. There's 2 types of liquid crystals, fundamental types that we know of. One is called a nematic. In a nematic liquid crystal, all the molecules line up head to toe in the same direction, but otherwise they don't make any pattern. They're like sunbathers on a beach in the south of France. They all line up in the same direction, but otherwise they're not more regimented. That's a nematic liquid crystal state. And then a more complicated one is a smectic liquid crystal state, where all the molecules are lined up, but they also make a periodic pattern. So this is like a regimental band or something. They're all co-oriented, and they make a periodic pattern. So how did we learn how liquid crystals work? And how did they become so revolutionary for our information technology? Well, the first thing we needed was genius, and that was provided by Pierre-Gilles Lejeune in the early 70s. He was able to work out the correct physical theory for liquid crystals. One of the key things, which he acknowledged, unfortunately he passed away a bit less than 10 years ago, but one of the key things he acknowledged himself, which allowed him to understand what was going on, is that in the early 1970s it became possible to see the patterns that the molecules make in liquid crystals by using phase contrast microscopy. Seeing what was happening was critical for him to understand what was going on in these compounds. Okay, so here you go. Weakly interacting vapor, strongly interacting fluid, liquid crystal, and eventually you get to an ice solid state. Now I'd like you to consider another situation. Here's a piece of copper wire. Inside the copper wire, there's a vapor of electrons which is free to move around. It's the thing which delivers the power to your house and throughout your house. Each wire is basically a tube with a featureless vapor of electrons moving around inside. And they interact with each other rather weakly in the ultimate form of their electron gas in these materials. Now, if you increase the interactions between the electrons, you get a state called a heavy electron fluid, which Piers Coleman described this morning. It's really a fascinating and exotic state. I won't have time to discuss it here. If you increase the interactions some more, again, you might guess that what you should get is a crystal of electrons. Wigner predicted that, or if you take the strong correlation point of view, Neville Mott explained that. But there's another possibility. Okay? Maybe there are electronic liquid crystals in nature. No reason why they should not exist, is there? Well, there's a reason why there are three reasons why they should exist, and they're called Steve Kivelson, Eduardo Fradkin, and Vic Emery. Unfortunately, Vic Emery has passed away, but I can assure you that Eduardo and Steve are alive and kicking. And in the late 1990s, they proposed that in these strongly correlated materials, if you relieve the traffic jam just a little bit, that's what this doped Mott insulator code means. You just take away a few of the electrons. Then, okay, maybe you get a metal, maybe you get a superconductor, but you should also get electronic liquid crystal phases. Following from the idea of Dijen, Steve Kivelson in 1998 and 1999 was urging me very strongly to pursue the idea of visualizing electronic liquid crystals. So how do you visualize electronic matter? Well, first thing you do is you take this device called a scanning tunneling microscope. It's got a sharp metal tip. You can raster, you can move that tip back and forth over the surface of the object you're interested in. You apply a voltage, a battery, between this sample and the tip, and some electrons will be transmitted by so-called tunneling through the vacuum, and you can measure the rate of that electron transport by using a current amplifier. Then what you do is you measure that current and feedback on the mechanical assembly, which is rastering this tip. And when the tip comes near an atom, it pulls back, and when it goes in between an atom, it moves forward. You do that by keeping the current constant. So these machines are great, as Peter said at the beginning, for imaging where the atoms are. So each dot here is a bismuth atom, each dot here is a calcium atom, each dot here is a strontium atom, each dot here is a uranium atom. They're wonderful machines. They're basically like an old-fashioned record player where you're moving a needle over the surface and getting a response as the needle responds to where the atoms are. The only difficulty is that for understanding and visualizing the quantum mechanical wave functions of the electrons, this machine is not designed for that purpose. We had to generalize the basic idea beyond this point. So we and other people in the mid-1980s were working with the following idea. If you stop rastering, you just stop this tip near the surface. This is one atom on the end of the tip, and that's one atom in the surface. You keep them fixed relative to each other mechanically. And now you ramp this you change this voltage, then the current will change. You take the derivative decurrent devoltage, that's called the differential conductance. You can show from theory that the differential conductance is related to the amplitude squared of the Schrödinger wave function. It's related to Born's predictor for what should happen due to quantum mechanics. So now the idea is that at this location, you can measure the amplitude squared of the wave functions, And you can measure them as a function of energy because you can vary the energy at which you're injecting the electrons here. That's done by the voltage between the sample and the tip. Okay, so to image the wave functions, then you have to do the following thing. You want to put your tip at the first atom and measure this differential conductance as a function of voltage. It's just an electrical measurement. Measure the current as a function of voltage and take the derivative. And write down the answer for the first atom. Then you move to the second atom and do it again. You move to the third atom and do it again. You get the idea? So there's about 30,000 atoms in this field of view. You have to do it a lot of times to get an image of this differential conductance. But once you have that image, what it represents is, it represents the Schrödinger wave function squared, Max Born's function, resolved by location. That's what this R is, it's where you are in the image. Resolved by energy. It's an image of the wave functions at this energy. But now you have it at every energy. So you can do this. Sweep through the different energies and look at the quantum mechanical wave functions in the material. And immediately you'll see that although the piece of material didn't change, the quantum mechanical wave functions are all different at different energies. So how can that be? I can tell you that when we had the first of all, this is very hard to do. Let me say that first. So this is hard to do. Suppose you have 512 by 512 pixels, and each spectrum is several hundred data points. That's about 50 million measurements. And you're doing it sequentially. You're not doing it in parallel. You're doing one at a time. So if you have to do 50 million of anything in one day, you have a few milliseconds per step. So when we first did this in the late 1990s, it took about 3 months to get the first movie. And it took about 3 years to publish it. And the reason is that when we would submit the data, I hope the referee is not in the audience. If they are, I apologize. The referee would say, well, look, are you telling me that the sample is disordered? Or are you telling me that it's ordered? Or are you telling me that it just has a handful of impurity atoms, and otherwise it's homogeneous? Or are you telling me that it's somehow strangely periodic? Or are you telling me that it's heavily disordered? At the level of classical logic, those are meaningful questions. But in quantum mechanics, they are not meaningful, right? The same piece of material can have different properties in terms of its quantum mechanical wave functions at different energies. It's like taking a photograph of this room using different colors of light. If you photograph this room in ultraviolet, you'd see one thing. If you photograph this room in infrared, you'd see probably a very different thing. So what we're doing here is imaging the wave functions and resolving them by the energy of the electrons. Okay. Now to do this, this was very well known to be difficult or impossible to comprehensively map all the wave functions. But luckily for us, we didn't know. I didn't know anything about STM, so I didn't know it was impossible. So when we did the calculations, we figured out what's required is to make a machine which can move the tip to each atom and then passively stabilize it at that location such that its vibrations are no more than the diameter of the nucleus, a few femtometers. And then move it to the next atom, and then passively stabilize it again, and so on and so on. In a room like this, the amplitude of motion of the acoustic noise, even when I'm not speaking, is on the micron scale, okay? So that's 10 to the minus 15, 10 to the minus 6, 10 orders of magnitude of suppression just to suppress the acoustic noise for the experiment to work. So we came up with a very boneheaded idea. Okay, it's an extremely boneheaded idea. If you want to suppress vibrations, you make an ultra-low vibration laboratory, which is a nested enclosure of concrete, acoustic absorbing foam, and then an internal acoustic chamber, which is on a separate foundation, which is sitting on shock absorbers. And then inside the internal chamber, you make an ultra-low vibration table, which has another set of shock absorbers, and then a refrigerator, which will cool the experiment down near absolute zero, so you take away all the thermal agitation as well. So in our labs, usually now, the motion out here is on the micron range. That's a fraction of the diameter of one of your hairs. Here it's on the nanometer range, diameter of DNA. By the time you get up here, it's on the few angstrom range. The RMS motion of this object is just a few atoms. By the time you get up here, it's a few by 10 to the minus 12. By the time you get down inside the machine, it's 10 to the minus 15. We measured that directly. These ultra-low vibration labs, oh yeah, now I was going to say. So when I first came up with this idea, I was at a certain institution which shall remain nameless, and I pitched it to the management and said, if we could just build these labs, we'd be able to visualize electronic matter at the atomic scale. And there was no precedent. So they basically said, go away. So anyway, let me skip over this. So I have labs of this type now. I have some in Cornell, and I have some in Brookhaven National Lab, and we have instruments like this. In the intervening 10 or 15 years, there's half a dozen major labs with these ultra-low vibration facilities, which now allow imaging of quantum mechanical states at the atomic scale. And here, in St. Andrews, in Peter Voll's group, they have recently built and got into full working order the first ultra-low vibration laboratory in the UK. He has stolen a march and everybody else in that regard. And now their experiments are also spitting forth amazing new results on the visualization of electronic matter. So certainly for the purposes of visualization, at the moment, this is the best way forward. It's expensive, but I think history has now shown that it's worthwhile. Okay. All right, now last thing I want to tell, how much time do I have?
10 minutes.
Oh, perfect, good time. All right, so personal motivation for me is high temperature superconductivity. There are two types of particles in our universe. There are bosons and fermions. Don't ask me why. But you can, in the quantum mechanical world, so here's a quantum mechanical particle in a box state. Let's say it has this energy. You can put as many bosons as you like in one quantum mechanical state, provided you remove the thermal energy. So here are all excited, high energy bosons. You turn on a refrigerator. Eventually they lose their thermal kinetic energy, and at the Bose-Einstein condensation temperature, all of the particles fall into a single macroscopic version of the lowest energy state. Enormous numbers are in the same quantum state. You can get a macroscopic quantum object. I'll try to show you a movie in a second. Fermions, you can only put one fermion in each state, so you would think we're finito in that regard, but in fact, you can pair two fermions in something called a Cooper pair, and then it acts as if it's bosonic, and so you can condense fermions in a similar way. Here are all these fermions at high energies. We turn on the refrigerator and cool this guy down. They're losing their kinetic energy as the temperature falls. What they do is they pair to form Cooper pairs now, and as soon as they form Cooper pairs, they make a macroscopic quantum state which is made of those pairs of two electrons. This is called a superfluid. This is called a superconductor typically. Superconductors allow transport of electrical information and power with zero dissipation. They're perfect conductors. Now let's see if I can do this. So first thing I want to show you is how does Bose condensation work. So good. Okay, so an easily acquired boson is helium-4. This is a bucket of liquid helium-4, and it's at a low temperature. It's somewhere near 4 Kelvin. And it's not in a Bose condensed state. But you can cool it by reducing the vapor pressure, the same way as when you go up to the top of a mountain, the boiling temperature of water is diminished because the atmospheric pressure is lower. If you lower the atmospheric pressure of the helium gas, the temperature will fall. So in the late 1930s, two groups at Cambridge were studying what happens if you continuously cool liquid helium-4 to lower and lower and lower temperatures. Watch this. Temperature's falling. You're pumping away the gas, so the liquid level also starts to diminish as the temperature falls. It's falling. The boiling's getting more and more violent, though. almost inconceivably violent at 2.17 Kelvin, and at 2.1695 something, bam, it stops. So what has happened there is that all of the helium-4 atoms in this bucket, which is as big as, well, it's bigger than a beer bottle, I can tell you that. All of the helium-4 atoms have fallen into a single macroscopic quantum state. That's a Bose condensate, one of the most fundamental states of matter. Now, superconductors, let's see if I can do this. Okay. Right. So superconductors are materials where all the electrons are in a single macroscopic quantum state. And they have the property, for example, that they will exclude magnetic fields by perfectly non-dissipative currents flowing around through them. So let's see what happens if we do this and close this. Okay. Oh, wrong one. There we go. So this guy's a piece of high temperature superconducting material. This is a permanent high field magnet. These guys shouldn't be here. And the magnetic field lines from the magnet interact with the dissipationless currents in the superconductor so that it can be levitated and manipulated with no contact forces between one and the other. So this is superconducting levitation. Many, many other strange and exotic phenomena are associated with superconductivity. Okay, let me just jump out of here and go back here. Yep. Now, superconductors were discovered more than a century ago, and they only do their magic at temperatures below a certain temperature called the critical temperature. So in Kelvin, here's 0 Kelvin, absolute zero, which is minus 273 degrees centigrade. So most of the superconductors studied for the first 50 years of the field were superconducting near minus 260, let's say, degrees centigrade. Not very useful. And at this rate of increase, it would have taken until another 3,500 years until we get room temperature superconductivity. So that would be a bit frustrating, at least for me. However, in the last 2 decades, 2 classes of high temperature superconductors, one based on copper and the other based on iron, have been discovered by Alex Muller and Hideo Hosono. And their critical temperatures have been increasing very steadily on these 2 trajectories, with the hope, the gleam in our eye, that we would reach the point of having room temperature superconductivity in the conceivable future. Why do we want that? Well, there are many, many, many very good reasons. So I work for the DOE, Department of Energy of the United States, as part of my research program. And they have a major program focused on high temperature superconductivity because there are many good reasons why we need that for our technology. We need it to improve power efficiency and stability. You don't need this so much in the UK. Your network is reasonably stable, but the North American network is a mess. So we need it. We need it for power bottlenecks to send more power to big cities. We need it for, we can't build a high voltage power line from every solar farm throughout the continent. We need a compact way to deliver power from arbitrary locations. We need more efficient power gathering machines. If we had high temperature superconducting information technology, your laptop wouldn't use any energy and it would work about 1,000 times faster, terahertz operating speed. Then for high energy physics and medicine and transport, we also need high temperature superconductivity. These 2 compounds are dominated by strong correlations. When we try to understand how they work, we start with a magnetic state. There's a magnetic moment of the electron on each copper site, and there's a magnetic moment of the electron on each iron site. We start in a magnetic state, we relieve some of the quantum mechanical traffic jam, the high temperature superconductivity appears. So this is in the copper-based. The iron-based is rather similar, although here the magnetism disappears first. Here it disappears at this point, and high temperature superconductivity appears. There are many similar features in these phase diagrams, but there's been a long-standing mystery as to what are these strange intervening phases between the magnet and the superconductor. So here's a cartoon version of that problem. You start with an antiferromagnet. It's something where the magnetic moment of each electron is down, up, and there's long-range order of that arrangement. That's not a superconductor. What you need is to get pairs of electrons to be spin down and spin up, but otherwise free to move. So somehow we need to turn off the long-range magnetic order, but keep the magnetic interactions between the electrons. People have known that in principle for 40 years. One of the grave problems for experimentalists is that whatever way you do to go from here to there are usually other phases in between. And recently, the question has emerged as to what are those other strange phases, and the proposal is that they're electronic liquid crystals. So in our pursuit of that subject, and this will just take a minute or two, in the case of iron-based superconductivity, here's another temperature versus electron density diagram. Here's the superconductivity. We're trying to find out what causes the superconductivity and what's the identity of this strange phase. Is it an electronic liquid crystal? Well, luckily, we were able to image the quantum mechanical wave functions of one of the first images of the wave functions in one of those iron-based superconductors. No, not superconductor, the non-superconducting state whose identity we didn't understand. And when we image the quantum mechanical wave functions, it doesn't look very impressive here, but what we were able to show is that all the electrons are free to propagate in one direction, and in the transverse direction, there are static electronic nematogens, like little molecules, just all living there aligned head to toe. We were able to find a change in the crystal symmetry and show that these nematogens would rotate by 90 degrees, and that the transverse direction in which the electrons can flow would also rotate by 90 degrees. And at that time, we said that the parent phase of the iron pnictide superconductors is an electronic liquid crystal, an nematic electronic liquid crystal. We spent much of 2009, again, if the referee's in the audience, I apologize, but this was very hard to publish because in 2009, there really was no concept that in the parent state of the iron superconductors, there would be a nematic liquid crystal. However, if you do a citation search now, you'll probably find 10,000 papers, because in the parent state of virtually all iron-based superconductors, we now know that there is a nematic electronic phase. So that's really good. This one is an electronic liquid crystal. So similarly, for the copper-based superconductors, we want to know what's causing the superconductivity and what is this strange state of matter here. Is it a liquid crystal? So here's an image of where the atoms are in a copper-based superconductor. And here's an image of the arrangement of the electrons. It's really quite different. They have self-organized themselves in a very strange way, in a way which had not been seen before. We can analyze that. There are two periodicities here. One is periodic with the crystal, and the other one is a longer wavelength periodicity, which is near 4 unit cells. If we analyze the periodicity of the crystal, we're able to show that inside every unit cell, the electrons on the east axis and the north axis, which had been expected to be in an identical state, were not. It breaks rotational symmetry inside every unit cell. And that's what an electronic nematic phase does. So this was the first direct evidence that there's an electronic nematic phase in the copper compounds. And if we look at these longer wavelength modulations, now you can guess what they probably are. They are periodic modulations of the fact that there's a broken rotational symmetry inside each crystal unit cell. And we can tell that because we know where every atom is. These black guys are the copper atoms. These blue guys are the oxygen atoms. And from that, we were able to discern recently that the periodic modulation is modulating the fact that already there's a symmetry broken inside the unit cell. So there's a nematic broken symmetry, or a nematic liquid crystal, which is generating a smectic liquid crystal. So in the copper-based superconductors, there's an intervening phase here, and it's got both broken symmetries that Dijen would have expected for a classic liquid crystal in the 1970s. So, where do we go from here? Well, now we know these intervening phases have many of the expected properties of electronic liquid crystals. for both classes of high-temperature superconductors, iron-based and copper-based. The challenge to our theory colleagues now is to understand what is the correct theory for the interplay of the electronic liquid crystal phases and the superconductivity. That theory will determine what we should do in order to improve the superconductivity. They might be competing with each other, in which case we should attempt to destroy this electronic liquid crystal phase, or they might be cooperating with each other so that the superconductivity requires this to survive. So at the moment, because many of these observations are new, the theoretical situation is not well established. But those are the main questions which are now on the table. What's the relationship between the electronic liquid crystal state and the superconducting fluid state? We would hope if we could solve that question to bring room temperature superconductivity one step closer to reality and one step closer to its potential economic benefits, which are great. And with that, thank you very much.
Thank you, Seamus. At the risk of delaying things a few minutes longer, there may just be a few people in the audience who have a question. No physicist to ask. Please.
What would happen if you created one of those superconductors with an antimatter? Would it create an opposite magnetic field?
Would what create an magnetic field?
If you created one of those superconductors with an antimatter atoms.
Okay. If you made a superconductor with antimatter.
Yeah.
Yeah, okay. So the theory for that is rather well worked out and understood. There would be an equivalent Meissner effect in an antimatter superconductor, but its sign would be opposite to the one we're familiar with now, because it would be positrons which would be carrying the charge through the antimatter crystal. So antimatter atoms and maybe even molecules have been made, but antimatter crystals are only made in the movies. They don't exist yet.
Thank you.
Okay, so the question is, if these guys are competing with each other, how would we increase the superconductivity? So I think that's a question for a theorist, but let me give the experimentalists a guess at that. So suppose you knew what this state was. You know the correct theory describing why this state exists. And you know from that theory why this state comes into existence. So you have a microscopic theory for why the electronic liquid crystal comes into existence. And the same theory would allow you to understand why the superconductor exists. With that theory, you would know which parameters, which knob you had to turn to amplify the superconductivity and suppress the electronic liquid crystal phase. So that's a very hard challenge, but if you look at the power we have over semiconducting materials now, if you order up a new semiconducting material having a new property for a new commercial device, there are people that can design those quantum mechanical materials and make them and have them work as predicted. So there are some areas of condensed matter physics which are predictive, perfectly predictive at the level of making billions of dollars. This problem, we haven't reached quite that point yet.
Please, back. Give your microphone.
If you used the electronic liquid crystal in new modern technology, what do you think would happen?
You're saying if you used electronic liquid crystals?
Yeah.
Oh, that's a brilliant question. So, I didn't have time to discuss this, but the reason why traditional liquid crystals are so useful in your telephone screen is that you can press a button and they'll change from one state to another. They'll change color or they'll change their pattern. An electronic liquid crystal, which was gated from behind, at least in principle, could be arranged so that you could press a button and it would change its properties. You could press a button, it would turn into a magnet. Press another button, it would turn into an insulator. Press another button, and it would turn into a superconductor. So once you have states of matter which are so close to each other and so delicately balanced, usually you can find a way, an engineered way, to convert one into the other. If that was the case, you wouldn't have to make electronic circuitry where you made all the decisions in advance, let's say to make a silicon chip. You could just make a general circuit which had some patterning at the back. And depending on what you wanted the chip to do, you could just order it to have the correct arrangement of conductors and insulators. So it's conceivable that electronic liquid crystals, if they can be controlled, could revolutionize electronics.
Just one last question. Right here, thank you.
I'm not a physicist, I'm a computer scientist, but I have a general question. Assuming that the solution to one of your important problems exists, which you haven't found yet,
Yeah.
what would you think is what to your opinion, is the major bottleneck to reaching that point, actually finding that solution?
Okay, great.
Money, time, maybe something?
No, that's a deep question. Thank you very much. Let me go back here to my traffic jam. That's really an excellent and deep question. Now, to predict what's going to happen in a classical traffic jam is already very difficult. Right? You have individual operators, and otherwise you have more or less identical vehicles on a well-defined region of space. But to predict when a traffic jam will occur or when it'll be relieved is actually very difficult, even in the classical world. The quantum mechanical version of that problem is exponentially more difficult. Nobody knows. So people know how to solve that problem if there are, let's say, well, Andy Millis may correct me, but if there are, say, 4 cars in the world, you could solve the correlated quantum mechanical problem. But if there's 1 million cars in the world, there's no mathematical and computing scheme known at the moment to solve that problem.
So we have a way to go. I think with that, this is a great time to stop. I should say to everybody that there are reception outside, drinks outside, everybody is welcome. And to thank you again, Seamus.
Thank you.
Great.